The last thing we need to consider in electromagnetic induction is the operation of a transformer. Now, a transformer is a device that is used in a lot of different applications. And we're going to start off just looking at the very basics. But we can describe a transformer as being something that transfers electrical energy. And it's going to transfer it from one circuit to another. While it's doing that, there's also going to be either an increase or a decrease in the voltage that's involved. That's going to be particularly useful when you think about power transmission, and we'll talk briefly about that towards the end of this video, and lots of other applications where you need that change in voltage from one circuit to another. So let's have a look at the very basics of a transformer. So the first part I'm representing here is the iron core. Now it's made out of soft iron, so that basically means that it's a material that's going to be easily magnetized, but it won't retain its magnetic properties once the current that's being applied to it has been removed. And you'll notice it's a little bit of a squarish sort of shape. The only reason I'm representing it that way is just makes it a little bit easier to show what needs to be shown. But they won't always be that sort of shape. This is just to get the idea across, to make it easy to understand how a transformer works. But important to recognize there that that's a soft iron core. Now, attached to that, either side, are going to be the two circuits that we need to deal with. So on this representation, I'm only going to represent a few coils that are looped around each side. So the circuit that we're dealing with here, it sort of looks a little bit like a solenoid attached to each side of the core itself. And this side we refer to it as being the primary coil. Now, as I said, we've only represented 5 coils there, but you probably tend to see more like sort of 500 or even 5,000, depending on the application. So NP represents the number of coils. This circuit here would be connected to some power supply or some other part of the circuit, and there would be a voltage VP across that solenoid. That would then give rise to a current flowing through that part of the circuit, IP, as well. Now on the other side, we're going to have a similar sort of setup. So we're going to have another solenoid kind of effect over here, but this time we're going to have more coils. And again, I'm only going to represent a smallish number. In real applications, you'd have far more coils around a transformer than what I'm showing here. But again, just to make it a little bit easier to make sense of what's happening in this sort of scenario. And this coil is known as the secondary coil. Similarly, we're going to have the number of coils now NS. The EMF that's produced between the ends of the circuit itself will be Vs, and we would therefore also have a current flowing through there given by Is. So there's the basic structure of a transformer: a primary coil and a secondary coil, both wound around a soft iron core. Now, to explain this scenario, we're going to make some notes and we'll add some more detail to that diagram. The first thing to be aware of here is that that current IP in the primary coil is going to produce a magnetic field. So we've already seen that if there's a current flowing through a conductor, and in this case a solenoid, there will be a magnetic field produced around the conductor, and given that we're dealing here with a solenoid, that means that there'll be a magnetic field inside the solenoid. That is going to have the effect of magnetizing the soft iron core. So because we have a soft iron core inside that primary coil, it's going to become magnetized. So what we can consider then is that there are magnetic field lines that will be looping around the inside of the solenoid through the soft iron core, so representing that just on sort of that inside surface, and in this case the direction of that magnetic field would be in that orientation. I'll just draw a couple more field lines to represent that as well. So one on the outer surface there, again flowing in that direction, and then we'd have the inner surface would be going this way as well. So hopefully you can see there that we've now got these magnetic field lines that are looping around that soft iron core, and now they're actually passing through the secondary coil as well. So the next point to make is that if that supply VP is AC, so an alternating current supply, that means that that magnetic field is going to continuously change direction. So it's going to vary backwards and forwards, alternating direction clockwise to anti-clockwise, and that's going to have the effect then of changing the magnetic flux through the secondary coil. We know that whenever we have a change in flux in a coil, it's going to produce a current. So the secondary coil experiences that change in magnetic flux. So a key point to note here is that a transformer requires an AC source in order for it to work. A DC source isn't going to produce the desired outcome because you won't get a change in flux. Now the change in flux, we can relate that back to the primary EMF VP. That's going to be given by Faraday's law, so that's equal to negative NP delta phi on delta T. So we can also then identify, due to Faraday's law, that the secondary coil is going to produce an EMF. So the changing magnetic flux through the secondary coil means that an EMF, Bs, is going to be produced, and that's going to be equal to negative Ns delta phi on delta T. And as I said, that's induced in the secondary coil. So in both of those equations, we have that term delta phi on delta T. And if we take that from the first equation and rearrange it, we'll find that that's equal to Vp on Np. I'm going to leave the negative out in front of the delta phi delta T. From the second equation, we'll find that that's equal to Vs on Ns. So we can rearrange that and look at the ratio then of the EMFs, so Vp over Vs, being equal to Np over Ns. That's an equation that's in the data booklet, so it's an important one to make sense of. Now, if Ns is greater than Np, then that's going to mean then that Vs is greater than Vp. So we've got an increase in the EMF. That's known as a step-up transformer. So the EMF has been stepped up, it's been increased. Alternatively, if we have Ns being less than Np, then we have that the secondary EMF is going to be less than the primary, and so it's going to be a step-down transformer. We can talk in a little bit more detail in class about those applications, particularly with reference to power transmission, but those two are quite important to make sense of in terms of the ratio of the number of coils and how it therefore affects the voltages that are involved. Now, if we consider the situation of an ideal transformer in physics and talking about anything that's ideal, we really mean that there's no energy losses involved. So in practice, transformers aren't ideal, but to make sense of the concept, it's easy to start off with the ideal scenario. we do have conservation of energy applying to all transformers, but with an ideal transformer, it means that all of the power that's input into the primary coil will be transferred to power in the secondary coil. So we're not going to see any losses of energy. As I mentioned, we are going to see losses of energy in real transformers, and I'll make a brief note about that at the end. But the key point here is that we have a scenario now that the input power, so I'll call that PP, is going to be equal to the output power PS. So the power in the primary coil will be equal to the power in the secondary coil. And hopefully you can recall that when we're talking electricity, power is given by the product of the voltage and the current. So VP IP is equal to VS IS. And that is a second equation about transformers that you'll find in the data booklet. The significance of that equation is that if VS is greater than VP, then we have that IS is going to be less than IP. So with an increase in voltage, we'll actually see a decrease in current, and vice versa. If VS is less than VP, we're going to see that IS is going to be greater than IP. So you can tie that back into the step up and step down transformers. Particular importance here is that when we have a low current, that means that we're going to see very low power losses. So really important for transmission of electricity. That's why we have high voltage power lines. With a very high voltage, we have very low current. And so as a result, it means that there's very low losses in energy through those high voltage power lines. To finish, as I said, in real transformers, there are actually going to be some energy losses. And as in most cases where energy losses are involved, some energy is lost to heat. And the heating that we're talking about here is mostly in the core itself. But in this scenario, we also have some energy lost due to flux leakage is the term that's used. And that means that some of the flux that's produced by the primary coil doesn't actually thread through the middle of the secondary coil. So there's a loss of the magnetic field strength through the secondary coil, and so therefore a loss of flux through the secondary coil. There are ways to minimize that flux leakage, but it's not something that we need to deal with in this course. But if you're interested, you could go and look that up. So there's the last bit of detail on electromagnetic induction. Hopefully that makes sense. We'll have a look at a couple of applications of that in class. And we have a small transformer that we can use to measure the output voltages for varying numbers of coils in the secondary coil.